Good to be back in Paris at the Origins 2026 conference with noted astrobiologist Vladimir Airapetian, who is with NASA Goddard Spaceflight Center. And in the interview just now, we did an interview. You were telling me about a new NIAC project that is actually ingenious, and it's a much cheaper alternative to look for potential exo-Earths that might, or at least a terrestrial mass planets around circling other sun-like stars that might have precursors of life. It's a shortcut. That's a pretty cheap shortcut, and you're working, I believe, with the noted Nobel laureate John Mather, who was the co-discoverer. He was a co-discoverer of the cosmic microwave background. Is that correct?
That's right, yeah.
So tell us about this project.
Well, this is an exciting project that provides the faster and cheaper and more efficient way, unlike the Habitable World Observatory, which is much more complex.
Which you said was going to be budgeted at somewhere
Sometimes
around
more expensive.
40 billion?
Yeah, right.
Okay.
But might be 20 billion, I don't know. So it depends, how it works normally.
But in this stage of iffy funding from Congress, it's, I know you can't say much because you're a NASA employee, but I can say 20 billion, 40 billion, that's hard to squeeze out from them. I mean,
Yeah.
So go ahead.
It's a little bit challenge, yeah. But so we are, of course, as a scientist, we need to go for something that is available now, something more efficient, and we know that, let's say, that extremely large, European telescope, the 30-meter telescope, is under construction now, and will be available in the early 30s. Okay, so the idea is that to build a so-called hybrid observatory, when we have a big telescope on the ground that can observe the exoplanetary system in optical light.
And you're talking about
light.
the ESO ELT under
Right.
construction
Exactly.
in the Atacama Desert.
Yes, ESO, ELT, exactly. And to use this as the, source of light, as a collector of light, okay, with this big mirror, and then the challenge is to block the star, this light from the star, to reveal a faint planet that billion times fainter than the star itself. So
Right.
we need to create like an artificial eclipse.
Right.
Okay, so
an occulter. You need
an
a
occulter.
You need an occulter.
So
in
we
orbit.
need an external occulter, and the idea that we want to place an occulter. It's a structure like 100 meters, it's about 300 feet large structure, at a distance of 175,000 kilometers away, which is about, 175 kilometers away. It's about like 100,000 miles away. Okay. And at that way, we can use lasers.
So you're talking about, would it be a geostationary? Would it have to be geostationary?
No,
or would
no, it's not geostationary. It's much farther away than the geostationary.
But you're talking about more than halfway to the moon.
Yeah, exactly. So, but this structure will get kept. We will create adaptive optics that will account for the atmospheric turbulence.
All right.
And we will be able to create this extra high resolution images and reveal the planet in optical light
By blocking out
out the central star.
The central star of the extrasolar planet.
Yes.
The extrasolar system.
Right.
And it seems very complicated, but this is a brilliant idea because you're going to be using existing ground-based optical technology in the form of the European Space Agency's extremely large telescope, a 30-meter telescope, that is going to come online scientifically. The first light, I think, is 2031 or 2032.
Yeah.
Something like that. And is it possible if you get the phase, you've already done phase A, you're applying for phase B, a phase B study, and this is what is it? The NIAC stands for what? Remind us.
NIAC is a NASA Innovative Advanced Concept. NIAC.
NIAC.
Yeah. So that they normally fund those revolutionary projects that have a pretty efficient output. Sometimes are kind of like bordering with science fiction.
Uh-huh.
But this is not a science fiction. It's a technology that have been already developed, and I'm so happy to work with the people from JPL who already developed the occulter. The people who is doing the material science, and they're developing those lightweight and sturdy structures that can be placed and moved from object to object, in an efficient way.
And we're not talking about a coronagraph that blocks the central light on the telescope itself. You're talking about something
Right.
that's placed, in orbit or close to it, or further on.
Yeah, but that's going to be a separate structure.
A separate structure.
A separate structure, standalone structure.
And can it be modified from the ground? In other words, you can move it from around the celestial sphere as you need?
Absolutely. That's the idea.
So it's going to have a capability to move with some sort of micro thrusters.
Yeah, and for that reason, the structure should be very lightweight.
Very lightweight.
Very lightweight. Yeah. So that's the idea, and I think that we're leveraging from the existing technology of the telescope that will be operational soon, at the same time from the technology of those lightweight occulters that were basically NASA is building for some time. So those two will be combined in one project that has a really great promise.
And if all goes well, when do you think we could see this occulter?
Well,
Actually,
according to our projects, in a few years, but 3 years, pretty fast. I mean, the idea
even
is,
before the ESO ELT is online.
Yeah. So
Okay,
basically, by the end of the 2020s, we will have that. Yeah.
So then the other last thing I want to ask you is it's another ingenious way of using existing samples, lunar samples from the moon, and I applaud NASA for the way it's curated the rock samples from Apollo. They've done a great job, and they've shown great foresight in the way they have kept some samples absolutely pristine because they were waiting on new technologies. They didn't want to disturb the samples. And so you want to use the lunar Apollo samples as a mirror to better understand our early atmosphere, early Earth, what?
Not exactly. I'm not going to use the Apollo samples. I want to use the samples derived from the lunar base.
From the lunar base.
From the South Pole.
Why can't you use the Apollo samples?
Because
there's some people who presented talks here.
Right.
Okay, go ahead.
Yeah. So the point is that I consider the Apollo samples are the samples derived from the sites of the relatively recent lunar volcanism, which occurred only 2 billion years ago. And 2 billion years ago, our sun was already kind of old sun, quiet sun,
okay.
and doesn't have any specific signatures to carry on. So that's why I don't think that it's very representative to uncover the history of our sun. However, if we move to the South Pole, especially to the permanently the permanently shadowed areas, regions, so-called PSRs, they are probably the best preserved regions, the most pristine lunar regions that will carry the memory of our sun and all those, explosive processes. And also might be some of the signatures of life from Earth.
Okay. Well, thank you so much again, Vladimir Airapetian at NASA Goddard. Thank you so much for your time today.
Thank you.